stream. Alright, the stream is technically up, so class has officially started. Believe it or not. I've been here for a long time. Adam and I have been here since like 4:30, and I feel like I've been here forever. Left work early to beat traffic. I don't know if it was a good idea or a bad idea, but whatever. I don't know if we have any streamers either, so I guess if you're streaming, say something. Alright, we actually, if you count today, only have 9 sessions left. We have today, Wednesday, Saturday, Monday, Wednesday, Saturday, and then a Wednesday, Saturday, Monday. Because I guess MLK Day we're not, Andy streaming. Hey, Andy. So I guess MLK Day we have off, and that's what pushes it to the next week. So, you can count on 2 hands how many sessions we have left, which is pretty crazy, right? It's been a long adventure. The rest of the class is pretty much going to be dedicated to working on your projects. We have some stuff to go over this week with, like, data structures and algorithms and all that. Today's lesson is supposed to be a lot longer than I'm going to make it. There's a lot of filler in it that I didn't think was necessary. For instance, the first activity, I thought it was a little ridiculous, says, have the students research the word algorithm for 10 minutes and tell you what it is. I'm not sure that that requires 10 minutes or any time at all. I'm also not sure why it takes 5 minutes to share responses and then 10 more minutes for me to define it. So that's 25 minutes we can just axe, and I'll tell you an algorithm is a set of steps used to solve a problem or a calculation. Boom, done. Condensed. That was nice. So, gonna skip that. Anyway, yeah, so most of the rest of the class, I'm going to go over a couple of little things. There's some exercises for you to do, but I'm probably just going to go over it, and we'll talk about it, ask questions if you want. I'm sure it won't take more than 30 minutes, and then we'll work on projects. Does anyone have any questions about anything, or concerns, or whatever? Cool. Alright, let me go ahead and open up this. I'm gonna make a new file. Alright, so getting into the very fundamentals of algorithms, I suppose. So an algorithm is just a set of calculations, a bunch of steps that make up a calculation effectively. So 2 plus 2 is an algorithm that leads to 4, right? It's not a very complicated one, but it is one. But algorithms aren't necessarily limited to math. A bubble sort we did near the beginning of class, that is also an algorithm for sorting, right? There's more complex sorting algorithms. There's searching algorithms, which we'll kind of look at today. All kinds of things. A for loop is an algorithm. An entire method is an algorithm. An entire application is effectively an algorithm, right? So if you really want a more broad definition of what an algorithm is, it's effectively everything that is a sequence of steps that lead to some final result. You know, there's probably a better definition out there than that, but that's good enough. The reality is, the stuff we're going to talk about this week is, I think it's important. I do think it is important stuff, but I can't teach it to you very well in 3 days. And I'm no expert. I didn't take a CS degree. You know, I'm definitely not an algorithms, data structures expert. Outside of the basics, you know, I'd have to Google it all and figure it all out again anyway. I can't, you know, make a red-black tree off the top of my head right now for you. But I can tell you a little bit about the important things. So things that I think are important, such as time complexity and stuff like that, which do come up sometimes to some extent in your work, right? And they will. So the most basic form of algorithm that I would like to show you would be like a for loop, okay? So say we have an array. We'll just call it numbers. And it's going to be really simple. 6 numbers, okay? There's nothing crazy about this at all. Actually, I'll make it even more complicated than that. I'll copy the one they have, which is a little longer. Okay, this one's like 14 numbers. A bunch of random numbers, right? And say we wanted to find a number in this list. the simplest way is probably to take that number and loop over every element in the array and see if they match, right? So we could have a number, say we have 311. So we can just do an of search, so for each with an of, right? So that's going to give us the values of the array. If the number is equal to the current element in the array, then we're going to console log we have a match, and we're going to just return. We're done. Right? That's it. It's the end. Or we could break. We're breaking out of the array and we're done, right? So I can go ahead and node. I can look through search and we have a match. It's not too important really to see it in action because we can all probably visualize it at this point, okay? So it's going to start with 10. So n's going to be assigned to 10. It's going to say is 311 equal to 10? Nope. Keep going. Is it assigned to 34? Are they the same? Nope. Keep going. Is it 56? No, it's not. Okay, keep going, right? So pretty simple. It's just going to loop through this to try to find a number. What this represents is what's called a linear search. So linear search, basically what we mean by that is as the number of elements in our array grows, so does the maximum time it takes to find that element in the array. So say I was looking for 514, which is the last item in the array. It takes us however many elements, it says I think it's 14, it takes us 14 searches to find that element, right? But if 514 was at the end of 100 million, an array of 100 million different elements, it would take us the time of 100 million searches, right? 100 million loops to find it. So the complexity of this application, or this algorithm, grows with the number of elements in that array. It's linear. It is directly proportional to the number of elements in the array. It's the most basic type of searching algorithm, right? Now, how do we demonstrate these kind of efficiencies and the growth in the change in how this algorithm works over time? There's actually a package we can use called benchmark.js that you can just install with npm that we can use to time how long these algorithms take, proportionate to how large the array is. So we have a little function. Now all this stuff is uploaded to GitLab. I uploaded all the solutions and everything for this week, so if you want to look at them, feel free. We have a function that's just going to go ahead and generate for us a random, an array of random numbers. So we'll give it a length. In this case, it's going to be like 100 million. We'll make it smaller. And it's going to just create a random number to pump into that array at every index effectively. And we're going to search for another random number and see if it matches. So we're just going to generate another random number based off the total size of that array and see if there's a match. And what we'll see is as this array size gets larger, so is the length of time it takes to search, right? It's a pretty straightforward concept at this point. So let's just make it 1,000. It's nice and small. We can just run node linear search, and we're going to get some numbers. So on average, the search took 2.99 to the e to the negative 7 seconds. So like effectively no time at all, right? It took almost no time to search through this array. However, if I change it back to 100 million, I actually have to call this with a special attribute here. This max old space size says, make sure you bump up how much space my node process can take, because if I didn't, I'll get a problem. So this array, this 100 million element array, is actually so large it'll crash my app. This is a V8 engine error. So what runs Node is called the V8 engine. It's something developed by Google that they use in Chromium, in Chrome, right? It interprets JavaScript and does a whole bunch of stuff. Whoops, sorry, I closed some windows. Whatever, it's not that important. Anyway, it takes your JavaScript and it runs it and does all that stuff. So what's actually happening is it's trying to generate a bunch of JavaScript, a bunch of stuff in memory in that array, and it's actually exploding because it can't even take that much memory before it crashes. So that's how much different this search is already. We have that many elements that it literally can't even run this by default. So how much longer is it going to take? Well, I have to put in my special parameter there so it can go up to 8 gigabytes in size. It doesn't need that much. It only needs like 3 gigs. Okay, it took 0.03 seconds. That's significantly different. That is much, much, much longer. But it's proportional to how many elements are in that array. That's what's important. So when someone says, hey, we have a linear search, you know, you can already deduce that if that array gets really, really large, or whatever we're trying to search through gets really, really large, it's going to be a really, really long search. So this begs the question of how can we be more efficient? One of the things in computer science that you learn, and the whole point of really the computer science degree, is to study these kinds of algorithms to find the most efficient ways to do these searches. Searches or sorts or anything really, it doesn't matter. Mapping, all kinds of different objects in memory or whatever. They just, the goal of computer science is to really find the most efficient forms of algorithms for us to do our work, right? We see algorithms like this all the time. You've written a ton of algorithms like this. You've written a ton of for loops in this class already, and you can imagine if you were looping over an array of elements, and for each element you render something to the DOM. When you get to 100 million elements, your computer is going to basically shit itself, and you're done, right? It's not going to be possible anymore. However, if you don't need to render all those things, or you need to find one thing, or you just need to quickly go through something to find a match, there are more efficient ways you can do it. So the linear search is very basic, right? We're just searching through each element. However, how can we make this more efficient? So technically at this point we're supposed to spend about 45 minutes talking about the linear search. Why don't I actually show you? There's a good visualization that can show you the linear search too and kind of how slow it is. Oh my gosh. And I do like it, if I can never drag it over to the screen. Okay. So we have a linear search. We have these two arrays, right? And right here we have element 348. So if I run the linear search, what it's going to do is actually go through each one at a time. This is exactly what our code was just doing until it finds the match. So that was pretty slow, right? If I change it to 670, which is element 221, I'll bump up the speed so it doesn't take forever. You can still see it has to go quite a long ways. Obviously on your computer this is instantaneous, but in our little visualization it has to go quite a long ways. So how do we make this more efficient? Well, there's other forms of searches. One of them that's very, very common that you're going to run into is called a binary search. Okay? A binary search, what it does is basically it starts in the middle and it says I'm going to check if whatever element I have in the middle is greater than or less than the element I'm searching for. If the element I'm searching for is greater than the one in the middle, I know I need to search greater than that number, right? Assuming my array is sorted. We're making that assumption right now. If it is, then I can just kind of cut the array in half, and I look at the top half now, and I can start in the middle of that. And you'll see the binary search is significantly different in the way that it starts parsing out this array, and it gets to the answer much faster. So it's already found the answer. That was significantly faster, right? This is a small kind of trivial example of what a binary search does. The important point is there are ways to be more efficient if you're trying to maximize how fast you find something in an algorithm, right? Again, why are we teaching you this? Basically to give you exposure to basic algorithms. Searching algorithms are not the only ones out there, as I've stated already. All right, so what if the data set's quite large? So I'm going to amp up the speed here. Let's do 644. It'll probably become much more apparent as the sets get larger how much more efficient the binary search is at finding stuff. So this is going to take quite a long time. Now, what was that? Yes, binary search is logarithmic, but you have to have a sorted array, at least for a simple implementation. Okay, so it took a while. Now we can do the binary search. It should be significantly faster. Yeah, it was ridiculously fast compared to the linear search. So what this introduces is something called time complexity, which we'll talk more about on Wednesday, which is what I think is one of the most important parts of learning these algorithms, is learning to understand what time complexity is and some of the ways that you can kind of make that more efficient. So Chris was just saying that binary search, that's logarithmic. So what we have with the linear search is it's linear, right? So every one element adds one more search to my entire algorithm, my search algorithm. So it's denoted with an n meaning for every element or n number of elements, it takes n time, right? So it's this proportionate amount. But the binary search is called logarithmic, which means that it only grows logarithmically in proportion to the number of elements. So it's a log n. And if you ever take a number and you do the logarithm of it, it's a much smaller number. So what that means is you get a far more efficient time in your algorithm. And that translates to more efficient code, effectively. I know I'm being very abstract about this right now, but we're going to go into it more on Wednesday. So, I mean, honestly, this class was... I'm going to show you a binary search. We're going to look at the linear search again. So, here's our linear search, right? So we're just generating a whole bunch of elements. Where this suite and add the function, this is to time it. And we're just simple for loop all the way through until we find a match. When we find that match, we're good, right? That's it. That's the entirety of this linear search through an array. It's, again, very, very simple, and it's a decent speed. Linear is okay. It's not the worst. For such a simple implementation, that might be all you need, especially if you can guarantee that the array is only going to be so large. So a binary search, how does that look? Why don't we take a look at it? So binary search, we have another large array, and in this case, we're sorting it. We're making sure that it's perfectly sorted, right? Because if it's not, this won't work so well, at least in this scenario. So what we do with the binary search, slightly different. We're going to start with the middle item based off of our min and our max index. So what's going to happen is we're going to start this search. We're going to say our minimum index is 0, so starting at the first element. Our maximum index is the last item in the array. Okay? And we're going to say while our minimum index is less than or equal to our maximum index, which is right now for sure, because 0 and is this like 10 or something, 12. We're going to take the element right in the middle of the array. So somewhere around here. And we're going to say if whatever we're looking for is greater than that element, then we know that the stuff before the middle point of that array is pointless. We don't even need to search through it anymore. So what happens is right here, say we search for 972, and it starts at 789 or even 212. So what's going to happen is we're going to come in here, our search element. This is going to be, we'll make it 1001, right? And then we have our array. So right here, it's going to pull the middle element, which is going to be 212. So we have if 212 is less than 1001, which it is, then our minimum index is going to be the index of 212, which is 1, 2, 3, 4, 5, 6, 7, 8, looks like. So now our minimum index is gone from 0 to 8. And what that means is everything before 212 is pointless. We don't need to search this anymore. So already just visually kind of, this is a great visual example, but visually you can see all of these elements in the array were just whacked off. I literally don't even need to search them anymore. Even if I was to do a linear search at this point, it's going to be more efficient because instead of going through 14 items or whatever, I'm going through like 8 or 7 total because I blew away half of them in the first search, and then I can go through the rest linearly if I want. But because of the binary search, we'll get even closer. So this time we'll go through, and the minimum one might be 1001, it might be this 4500. In which case, it's going to say, okay, well, our maximum index is going to be moved down to here. So now we're between these two, right? So we can go through it again and find the efficient one in there, and you can see it takes like 3 or 4 iterations to get through this whole array as opposed to 14. Potentially 12 or however many 10 this is. So that was a quick introduction to basic algorithms. Again, all of this stuff is in GitLab, so if you want to look at it and play with it. The exercises for today were literally to create a for loop and search through it, and then to do this and try to make it not explode, and you do that by adding that flag. So there weren't very many exercises today, and I don't think that they were very useful. There wasn't even a binary search exercise, which I think is more useful. I do recommend that you look at this binary search and kind of how it's implemented, kind of get a feel for it, maybe play with it a little bit before you start working in your groups, and walk through it. We could debug through it, actually. That might not be a bad idea. Why don't we debug through it? You can see how it works. Okay, so we have this array, and we're searching for 77, it looks like. So our search element, 77, we have this array. I will go ahead and set through these. We have a maximum index of 13 and a minimum of 0. So the minimum index is, of course, less than 13. So right here, we can go ahead and we can get the middle number, which is going to be 6. Grab the element at 6, which is going to be 211. So we're right here, and we're looking for this number, right? It's going to say, is the current element 211 greater than the search element? The answer is correct. That is true. So we can take our current index, which is 6, and we can move our max index down to 5, right? Because obviously 211 wasn't a match with 77, so we just move to right here and say this is our new maximum. Our minimum is not changed. The minimum index is still less than 5. So we could grab the new middle, which is 2. It's 43. 77 is greater than 43. Okay, now our minimum index can jump up. So we're between 3 and 5 now. So what is it going to grab? 4. Bang, we have a match. So 3 iterations for this one as opposed to this would have only been 5, so it's not that great of a win, but you guys saw the visualization. It was a big one. All right. Any questions on the algorithms we looked at today? Does anyone want any more explanation of any of this stuff? I'll Slack out this site that you can play with. Actually, it's kind of cool. We can open the Slack. Because if you do want more explanation, I'm more than happy to go into it deeper. We are going to cover this more in depth on Wednesday, a little bit more on Saturday. But again, while this stuff is very important, I don't think that we can really hammer in like calculating time complexity and some of the other cool algorithms we'll see, or you could potentially see in this class. One last thing. So the time complexity I was talking about with the linear search, you often see something like this. That O with an N in parentheses. So this means it's a linear search, right? It's called big O notation. We're going to talk about it again more on Wednesday. That linear search is linear by the number of elements, which is N. And then the binary search is log N, so it's logarithmic based off of N. You'll see this in computer science and stuff. And then there's the best form, which is O of 1, which means no matter what, you can always find it in one operation, right? So that's what we always strive for, but it's not always the case. There actually is an algorithm all of you already know and have used thousands of times by now in this class that is theoretically best case scenario O of 1. Does anyone know what that is? You know what it is?
Yeah, it's doing a front method to find something in the SQL database.
I don't know if SQL is necessarily O1, but in the best case it is. That is a good example. It's probably very close on most optimized indexes.
What was the question?
What algorithm have we used in this class already that is guaranteed best case scenario to be O of 1? Time complexity. Which means it takes one operation to find what you're looking for. Anyone have an idea? That was a really good guess. You're really close.
Boolean?
Boolean? technically, but I'm looking for a more complex one than that. So there's a lookup. So we have a linear search, right? We have this binary search. There's actually a lookup that we can perform in JavaScript that's best case scenario O of 1. It's an object. If I take object and I look for A, I guarantee to find A, right? I know its index, it's A. Immediately I get the value 10. This is a map. Maps are best case scenario O of 1. Not always. Worst case scenario log n. But it's an aside. It's just interesting to me, though. I thought it was very interesting when I first started getting into JavaScript that this object lookup syntax right here is effectively a map. And maps are incredibly important, and they're one of the few data structures you use a lot in programming. You do use maps a lot. Anyway, any questions on any of this stuff? It was kind of a tangent there. Cool. Send us your deliverable number 1. The way I have 2 groups I think I've seen so far. Jesse's group and Jake's group. So there's what, 2 more groups? Nor your group and then you guys' group, right? Cool. So send us your stuff. Otherwise, feel free to go work in your groups. And what you use them for? That's a good question. I don't know. So part of learning the algorithms is learning when to use them and why you'd want to use them, right? So that's a good question. That big O cheat sheet might have it. Let's look. It has some. So it has kind of some of the algorithms that you can use and their times. Best and worst case scenarios. And that's what you want to use. You want to use the worst case scenario to determine which one to use. There's more to it than that, but basically if you find an algorithm that fits your need and it has the best worst case scenario, that's the one you probably want to use. Probably they use some of these algorithms. Yeah, probably.